Hello everyone, welcome back to Physical Geology 1403. Today is lecture 11. We are discussing shorelines and the ocean floor. This is the last lecture of module 2. Okay, so per the democratic vote that we took last class session, you will be having your lab exam open today, and it will remain open through the weekend. Okay? You can take that here in the classroom, or you can take it entirely online, depending on where you think your time is best spent. Online students, obviously, taking it online is probably the option you're going to go for there. You are going to be getting exam 2 on Tuesday, next time we meet next week. That session is going to be an exam review for you, and then the exam will open and remain open until Thursday morning, because that's when we start module 3. The week after that, you get the last lecture of the class, and then the last day of class, the following Thursday, we will have our final exam review, and the final exam will open and close the following day. All right, that's where we're going. That's where we're at. Any questions about that schedule? Yes?
On the final exam, can we use notes?
Yes, you can use notes for every single one of these exams, including the lab exam that opens today. I want you to use your notes. I want you to consider your notes your greatest friend. I want you to cultivate them, grow them like a garden that your life depends on. Yes?
So one of these rocks is going to be in the lab?
Potentially. The lab exam, The lab exam is going to have 12 samples on it, 3 from each of the 4 identification labs that you have done in this class. And I'm even really nice about it. I straight up tell you, this is a sedimentary rock. This is an igneous rock. I tell you what type of rock it is already. And I ask you for the properties. It's on you to find the properties and identify what that rock or mineral must be based on those properties. Okay?
Is the exam 2 going to be like the second half of what we learned, and then the final exam is going to be everything?
Yeah. Exam 2 is just going to be over what we have discussed in Module 2. So the 3 lectures we have done prior to today, running water, groundwater mass wasting, glaciers, deserts, and today's shorelines and ocean floor. That's all that's going to be on Exam 2. It's actually, there's a lot of water questions. Sure, maybe, potentially. And it's because it's only going over half the content volume, it's only half the size. Exam 2 is only 20 questions, okay? Which is why I don't feel so bad about giving you Tuesday afternoon and Wednesday to take it, right? Because it's going to be really short. It's half the size of the first exam. But yes, the final exam is cumulative, which means that it covers all the content in the class for modules 1, 2, and 3. Yeah?
How many questions are on the final exam?
The final exam will have 45 questions. Not that much bigger than exam 1, which had 40. But it's cumulative, so it'll cover potentially the entire content course. Great questions. Anything else? You know I love questions. Keep them coming if you have them.
How would the lab exam be online?
How would it be online?
Yeah, like,
The same way that the labs are online.
so it would be like those YouTube videos where you're like going through like the...
Yeah, well, so there aren't YouTube videos for the lab exam. Otherwise, people would share my lab exam videos prior to taking the exam. The videos are hosted in Blackboard itself, okay? Each video for each question on the exam. And if you take it in person, I will give you a tray of samples that you can do your own tests on.
Or we could also come in, like in class?
Yeah, come in class. You can stay after class today if you want to take it. By the way, Giovanni and Javier, did those emails work out for you guys okay?
I haven't seen the teachers.
You haven't seen the teachers yet? Okay. If any of you guys want to talk to whoever's in charge. I don't know who you have to ask about this. But if you want to take the lab exam today and you get permission to do so, just come back and I'll give you the set and you can take the lab exam here in the classroom. This is your space. I want you to think of this as a sacred space for geology and studying. All right? Wonderful. Yes?
Is the building like open like Friday and Saturday or?
Great question. This building remains open on Fridays until 1 p.m. Technically, the college is closed after 1 p.m. on Fridays. I am always here. I'm here 9 to 5 on Fridays because I just have that much work I need to do, even though the college is closed. So if you want to come after 1 p.m. on a Friday, you'll need to arrange it with me beforehand so that I can go downstairs and prop open the front door for you, because it will lock itself at 1 p.m. Okay? I'll just be up here. And on Saturdays, it's usually closed because we don't have... There are some courses that teach weekend classes. I don't think we have any this term, though, because when I've come in on Saturdays to feed the snakes, the doors are usually locked. Good questions. What else? Yeah?
Will the exam like last time have like questions where you type out?
The lab exam is exclusively identification. Okay? The exam 2, yes, is a mix of those usual suspects I told you about before, including short answer questions. Yeah?
Oh, there's no short answer questions in the lab?
On the lab exam? I don't think I've included any in there. I've had the same lab exam for like the last 4 years. And I haven't really added anything to it. I've just changed the format a few times. So, no, there are no short answer questions on there. What is that? Is that like a super hot Funyun? I didn't know they made those. I don't eat chips that much. All right, what else? Okay. Have you guys heard of anything cool or fun that you want to share with the class? Any interesting science or stories in general?
We had a story that you wanted to do.
Oh, yeah? You've been volunteered.
I don't have it.
You don't have a story? That's fine. I've got one. Actually, it's not a story. It's not really a story as much as a hypothetical question. Okay? How many movies, books, TV shows, I don't know, songs, all of these different types of media have talked about, theorized the ability to stop time?
A bunch.
Yeah, it's in a lot of stuff, right?
Is that even possible?
Oh, I don't know. But let's talk about it. Let's assume stopping time is possible. Do you know what light is?
It's the
Huh?
sun rays.
Light, what we perceive as light, are actually photons. It's a particle called a photon. Well, it's a particle and a wave, right? It's weird. It does both, okay? What we perceive as light is actually photons, which, yeah, in our case, are emanated by the sun. They interact with an object. The wavelength of light that is not absorbed by that object is the color we see. So in the case of most plants on our planet, they are what? Green. Because billions of years ago, when these early organisms, the ancestors to plants, were developing, they developed with the ability to absorb all wavelengths of light for photosynthesis other than green. Green is the one color that they do not absorb for photosynthesis. And therefore, because it is the wavelength that is reflected off of this object, it's the color we see. Interesting. So what does this have to do with stopping time? Bless you. A photon travels at the speed of light, which means that if you were to stop time like that, would all photons stop? You would think so, right? And if that's the case, do all the lights just suddenly go out? If I could stop time, if I could have that Harry Potter time turner, if I could cast a spell, if I develop some piece of technology, everything goes black, right? Because the photons stop moving, stop reflecting. I don't know. What a fascinating thought, though, isn't it? Has nothing to do with geology, just very interesting science. Something to think about, ponder. Yeah?
The photons, this might be silly. Maybe I haven't thought about it fully, but wouldn't it just be like, wouldn't, instead of lights just going out, you just see one still image, and that wouldn't change? It would just be that still image. You're not getting any new photons.
Not getting any new photons, but still receiving. The problem with that is that there's never any one moment when you're not receiving something, right? Some wavelength is being reflected. If all of a sudden something was, it's not like one photon is bouncing to your retina. It's a constant stream of photons that are bouncing off of objects and being absorbed by your retina so you can see the color, right? So you stop that stream, you stop receiving anything. You don't perceive anything. The absence of all color is black. So, and to add another level to this plot here, a photon travels at the speed of light, right? We already established that. That's the fastest any object can go. Do you know how we define time? Time is defined by the speed of light. It is only by the fact that photons travel at the speed of light that we perceive time at all. All time is relatively based on the passage of particles of light, photons. So if you stop time, does the photon even stop moving? As far as a photon is concerned, because it travels at the speed of light, a photon is emanated by the sun and then immediately, in that same instant, absorbed by something somewhere else, even if it's across the universe. As far as the photon's perception is concerned, it was instantaneous. Only to those of us that travel at less than the speed of light does time exist. I know. Crazy, huh? Mind-blowing stuff. Mind-blowing stuff. All right, should we talk about some geology stuff? Move on to the actual subject of this class. Huh? Just have a fun day today? Oh, today can be fun, and we can still learn about geology. I hope that we have some fun in here every day you guys are here. All right? Even if it's with me talking about crazy, wacky quantum physics. All right? Okay. Someone remind me what the meaning of dynamic is. Let's start with that. Always changing. Thank you. Okay. A dynamic thing is something that's always changing. Shorelines are always changing. Okay? Shorelines are dynamic. Do you think when this road was built here, they knew that was going to happen? It's not supposed to be like that. Well observed, okay? Well, do you think when these houses were built here, they knew that the ocean was going to go and flood them? No. Look, they're on stilts. No one in their right mind would spend hundreds of thousands of dollars on a house with the intent of putting it on stilts. Okay? You'd have to be insane or have a lot of expendable income. Maybe Trump would do it. Okay? No. These are all things that have happened since those objects were put in place. And this can happen quickly. Right? What is the force, or not the force, excuse me, what is the process or processes, do you think, that are causing this to happen?
The water rising,
Sure, rising water, erosion. This cliffside crumbling away, getting destroyed. What process could that be? Weathering. All these concepts that we've talked about already, building up to this. Now, shorelines are right there next to the ocean. The ocean does not stop moving, right? Right? The ocean is always... How many of you have not been to the ocean? Never been to the ocean? Okay, most of you have been. Highly recommend going someday. Highly worth it. Okay? I spent most of my life next to the ocean. I miss it. Yeah, close enough to see it for most of my life. With the exception of 3 years in Ohio, my 2 years getting my degree in Idaho, 1 year in North Dakota, and 1 year in Montana, and the last 5 years here, the rest of my life has been next to the ocean. Yeah, I love it. Well, I was a Navy brat, right? I grew up, my dad was in the Navy for 23 years. So being next to the ocean was kind of a requirement of the job, right? So I love the ocean, and I miss it a lot. I go and see it whenever I can. But what's happening here is the ocean does not stop moving. It does that back and forth of the waves. We have currents, we have tides. It does not stop moving. And all of this is going to move, remove, or add material along these shorelines. Here you can see in both these pictures what happens when it's removing material. The shoreline is moving inland as a result of this. So this can happen by removing material, or someone pointed this out earlier. What's the other reason why shorelines could move inward? Huh? It could have to do with tectonics. The moon? Okay, the tides in the moon. Believe me, we're going to talk about tides in the moon. Okay, we'll get there. Hold that horse. All right, but what did you just say? Glaciers melting, which is doing what? Making the water go higher. Sea level rise. By the way, Aaliyah, good tectonics absolutely comes into this, and we're going to see that. There is a way that that happens as well. But what I'm looking for is rising sea level due to addition of water into the ocean, which usually comes from melting glaciers. Yes. Okay, so shorelines, constantly moving. Okay, so this is what I mean when I'm talking about a shoreline. All right, we have some different names, some different terminology for the different sections of our shoreline. Here we have the ocean out here. Generally, bless you, we call the deeper oceans, like further offshore, is, yes, offshore. That's what we call that. The near shore is where you start to have that rise up into shallower water, kind of going towards your beach, okay? And that goes all the way up to the low tide shoreline. Low tide, high tide. What are tides?
Waves.
No, waves are different. What are tides?
Oh, tides are
Not the pouches you throw in your washing machine.
tides in your water. Frequency of the waves.
Tide, bro.
Like little things.
The pop. Yeah. Tide. It's a kind of laundry detergent.
I thought you just like
Jackson clearly doesn't do his own laundry.
I do think it's 5 little pods in there.
He uses gain. What a loser. No, I'm just kidding. All right, what were you saying?
Is it like the frequency or I mean the force of the waves?
It's not the force of the waves. It doesn't actually have to do with waves at all. We talk about tides in a little bit, but I just want to give you... The tides are the... Okay, so the edge of the ocean goes away further from shore at certain times of the day and closer to shore at other times of the day. And this is based on what?
The sea level dropping, or like the ground.
Sea level's not actually dropping.
Not the sea level, like the ground is going down.
Why is the water doing this? It's the moon. It's not only the moon, though. It's not only the moon, though. Everyone's like, oh, yeah, the moon causes tides. Well, it causes most of it. But if our moon disappeared today, if it just went, whoop, gone, bye-bye, for some reason, the moon disappeared, first of all, the panic that would ensue, right? Second of all, our tides would still exist. A lot of people don't realize this. Why would our tides still exist? The moon's gravity causes most of our tidal surge, but not all of it. What's another nearby force of gravity that could cause that?
Or like larger objects?
The sun. Even without our moon, we would still have tides, dictated by the sun instead of the moon.
So would it be like high tides at different times?
Different times, different lengths, only about 30% as strong as the tides we have now. The moon is the largest gravitational force that causes tidal surges, but with the sun is powerful enough that in the absence of the moon, we would still have tides, only about 30% as strong as they are with the moon.
The water would go back
it would go back less and forward less. The tidal differences between high tide and low tide would be way different. So I'll tell you why this happens here in a couple of slides. But for now, let's just say at low tide, the water goes out, and where the low tide marker is, that's where our low tide shoreline is. That's where the near shore ends and the foreshore begins. The foreshore is between the low tide shoreline and the high tide shoreline. Okay? And then right here, this is part of the beach in the foreshore. This is where you go to build your sand castles. It's got the nice wet sand. That's where you go to play with your sand, right? If you want to build something. Out here, past the high tide shoreline, is called the back shore. This is where you go to set up your blanket and your umbrella and your chair to read, because the water is never going to go out there, right? It's never going to mess with whatever you put on the sand out there, okay? This is where you go to bury your brother in the sand, right? I had a lot of brothers. I buried them a lot, okay? And then back behind that is what we call the coastline, okay? This is your coast. Past wherever the water never goes. This coastline, that's typically the furthest your water would go in an extraneous circumstance like a severe thunderstorm or something. A severe hurricane could push your water as far as that. It doesn't go further than that. Your coast is anything past that severe waterline mark. Okay? So this is how we break up the different parts of our shoreline. Offshore, near shore, foreshore, backshore, coast. So when I say shoreline, it's kind of a moving target. I'm actually referring to this, generally, I'm referring to the foreshore area, where it is currently moving back and forth between high tide and low tide, okay? Just think of me as saying that area whenever I say shoreline today, all right? So, waves have a lot of influence on the shoreline, how it is shaped, how far inland it goes. Is it made out of rock? Is it made out of sand? A lot of this is determined by wave activity. Waves carry a lot of energy in them, which means that they are transferring a lot of energy to whatever is on our shoreline, be that rock or sand or whatever it is, okay? They carry a lot of force, okay? As much as 10,000 kilograms per meter cubed of water, right? Yeah, there's a lot of force that goes into this. Those of you that have been into the ocean, have you ever walked out far enough for the waves to hit your knees? I mean, yeah, it might knock you a little bit, like, okay, no, I'm good. But then you walk further out so that the waves are now hitting your stomach and chest. What's happening? It's knocking you back a little bit more. Why?
Because the further you go out, the harder the pressure is?
No, it's the same wave out there as it was closer to shore. You've only walked out maybe 10 or 12 more feet.
Oh, because it's like losing pressure as the further it comes in or something?
Nope.
Or not pressure, energy?
It's the same wave. It's not losing anything.
The energy, like the impact it has on.
What's changed? Has the energy of the wave changed, or has something about you changed? Yeah. It doesn't have so much to do with the center of gravity as much as something else, but you're getting a lot closer to the right track. The wave isn't changing.
It's where we're at.
This part of your body that it's hitting is changing. What's the difference between your legs at your knees and your stomach and chest? I'm not talking about the biological difference. I'm talking about the physical difference. Clearly, there's a biological difference between your knees and your abdomen. Surface area! You have way more surface area up here than you do down there. So the same wave hitting more surface area is going to transfer more energy into you and knock you back even more. Right? Makes sense. Now imagine all of the energy that wave is transporting onto a beach surface or a cliffside. All of that energy slamming into it over and over every day, 24/7, 365, millions of years. That's a lot of energy that's getting transferred into that surface and causing all of these changes. It's no wonder that shorelines are constantly in motion, constantly changing, constantly breaking apart, right? It's a force, it's an action that's just, it's always ongoing. The ocean is the greatest force for change, natural change, I think, in our world, right? Simply because of how much area it covers and how much energy it's constantly transferring into the materials around it. Okay? There's also the aspect of abrasion. Abrasion is when waves carry something and that something crashes into something else, right? Like a wave carried rock slamming into a cliffside. So you're not only getting the transfer of energy from the waves into the cliff, you're also getting another rock slamming into it. What's that going to do? It's going to break stuff off. Mechanical weathering, right? Slamming into it. Particles slamming into other particles, causing mechanical weathering, the physical crushing, breakdown, shattering effect. Okay? So let's talk about the mechanics of a wave real quick. There's this common misconception that a wave is water that travels across the ocean. It is not. It's a fanciful notion, very fun to think of. You stand on the coast of California, a wave hits you, and you think, oh man, how special. That water traveled all the way from Japan just to slam into my feet. It doesn't, actually. The same water generally stays in the same spot unless it's being carried by a current. The currents are what circulate water around. Waves do not circulate water. Waves only circulate energy. How does this work, you ask? And I say, excellent question, student. Let me explain it to you. All right, so you get wind out in the ocean. There's a lot of wind in the ocean, okay? This wind traveling above the water is going to transfer some energy into the top surface of that water. As the wind, say is blowing that way, transfers some energy into this top layer of water, that water is going to start rotating in a cell. Okay? It's going to start rotating in the direction that the wave or that the wind transferred energy into it. And some of that energy is going to transfer into the water underneath of that cell and make a second smaller cell. And so on and so forth, until what you end up with is a column of circulating water with that energy all the way down to the point where the energy kind of dies out and there really isn't any motion of water past that point. But this column of circulating water, that's what's moving. And again, the water doesn't really move. It's the energy cell rotating over and over, wheeling itself through the ocean in the direction the wind blew it. So this column of energy is traveling that way. The water generally stays in the same spot, again, unless there's a current involved, okay? So this column of energy, wherever you have that column of energy, there is the crest of a wave, and between these columns of energies is the trough of the wave. This is what a wave does. That's why when you're looking at a boat out in the ocean, you'll see it stays in the same spot. It just goes up and down with the waves because it's not the water under it that's moving. It's the energy that is causing our water to go up and down in these columns and troughs. Okay? So, what's happening here as the wave reaches our shoreline? Well, here we have our column of energy, right? It's traveling across the ocean, but the ocean floor is rising because it's coming closer to land. As it gets closer to land, that base at which there is negligible energy in that column runs into our shoreline. As soon as the bottom of my column of wave energy runs into that shoreline, that ocean floor, that sea floor, that shoreline floor, near shore over here, starts absorbing the energy from the bottom of my column. So our wave starts to pick up sediment. It starts to get a little sandy, okay? A little dirty. There's always stuff in these waves. It's starting to pick up sediment. The more sediment it picks up from the bottom, the less energy it loses, or the more energy it loses at the bottom of our column. But the top of our water column doesn't know what's happening at the bottom of the water column. It's still traveling at about the same speed. So what starts to happen is as the bottom slows down and the top keeps at the same pace, our column of energy starts to tip over. And that's what makes our crests as the waves approach the shoreline. What surfers like to go through, right? The nice cresting wave is our column of energy tipping over and finally crashing down onto the shoreline. That's what a wave is. Any questions about that? Wonderful. Okay. So, what does this do to our shoreline? Well, as the constant back and forth of waves is going to cause motion, transport, and breaking down of the material that's there. It is very rare for a beach or a shoreline to be exactly perpendicular, like 90 degrees, to the direction of waves. What do I mean by that? The statistical likelihood that any shoreline is going to be at exactly 90 degrees to the direction of wave impact, very small. Far, far more shorelines are at some angle to the direction of the approaching wave activity. What this does is it creates an effect called longshore current, okay, or longshore transport when it comes to describing the sediments involved, okay? So here we have a shoreline right here, and our waves are approaching at this angle. As our waves are approaching at that angle, they crash over onto the shoreline, the water washes up onto the beach until it's out of energy, and then what happens? What happens to the water from each wave? As it washes up onto the shoreline, it stops, and then what? Yeah, it slides back to the ocean, except it's lost all its energy. What is giving it the energy for that motion now? Gravity. And gravity pulls it what way? What's the closest it can get if it can't go down? Downhill at what? Huh? 90 degrees. So the waves are pushing water and sediment up onto the shoreline at that angle, whatever the angle of approach was. But after it loses its energy and gravity takes over, it falls back off that beach at 90 degrees. And then the next wave pushes it up. And then after it loses that energy, it comes back at 90 degrees to the plane of the shoreline. And so what happens is you've got this back and forth, but the gradual motion of all of this sediment that way. Okay, that's longshore current. Okay, yeah.
How does you know how there's like just a big old bar of sand in the middle? Like whenever you get further out, what's that called?
We're going to talk about that today. We're going to talk about that today. Yeah. Oh, is that not a question? Yes, of course. Okay, so longshore current carries sediment further down in the direction that the waves are traveling. Okay. That's why when you go to the beach and you see that some dummy left their styrofoam cup too close to the water and it got carried out, it doesn't just keep staying in the same spot. You see it gradually moving with the waves down the beach, right? That's that longshore current. All right, a few other features that we see on shorelines. Wave cuts, okay? So when you're looking at something like this, what you were seeing is at low tide, this surface is exposed. At high tide, it's going to be covered. But what's happening here? Clearly, there's been a substantial amount of weathering on this cliff surface, pushing this cliff surface back and leaving this surface underneath the wave base. Well, let's say sea level drops. If sea level were to drop, all of a sudden, this wave cut platform becomes the new marine terrace, and wherever sea level is now is out here weathering this new marine terrace backwards. And then sea level rises, boom, 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 boom. Maybe this is our new wave cut platform up here. We see this kind of step pattern on a lot of Earth's coastlines, and we can use those to interpret past sea level changes. Okay? Obviously, there's a tectonics aspect we have to take into account. Maybe this was tectonically lifted instead of it being sea level. Maybe it was tectonically dropped, right? But we can look for other pieces of evidence to figure that out. Okay? Sea arches. This is a sea arch. These are actually pretty common. We will see this wherever a particularly strong current has weathered away material in one part of a cliff more than in another part. Okay? So if longshore current is pushing a certain direction, we may see something like this where this all got weathered and crumbled away faster than the rock on either side of it. It also may have something to do with the rock itself. Maybe that was simply a weaker section of rock. Maybe there was a fault there. Maybe there's any number of things. But we get these sea arches showing up quite often. A sea stack looks like this. It's kind of just a tower of rock hanging out just off the coast. This most commonly forms when a sea arch loses the arch. What would happen if enough material was removed from both sides of this arch? What would happen to the rock in the middle? Why? Why would it fall? And we call that? No, what do we call it when material falls because it loses its support? Gravity's the force causing it. What do we call it when the material falls as a result of gravity? Angle of repose was in the same conversation. What's it called when something falls under the influence of gravity because it loses its support? It cannot be held up anymore. Mass wasting, yes. This will fall down under the influence of gravity if we remove enough of the support from either side. And when that happens, it just leaves a sea stack out there as the abandoned side of that sea arch. Okay? Then we have barrier islands, yes. We have barrier islands. Are you sure you want to leave? We're talking about what you wanted to talk about now. Okay, so a barrier island forms when sediment is built up off the coastline of a shore, okay, or off the shoreline. So here's our shoreline. This is kind of a top-down view. See, here's some buildings. I'll just make it clear that this is a shoreline. Boom, boom. See, there's a house. That's clearly a house, right? All right. The waves are coming in that way. All right. Now let's do a side view. Here is the shore. Here's the water. Here's the house right there. Okay, there's a nice door. Cool. Should we give them a window so they can have some light? Nice. All right, good deal. Our water, our waves are coming in like this, let's say. Okay, so this is our normal wave base. Yeah, sure. What about if there's a storm? Do you think a storm causes more energy in our waves? Yeah, that's why the waves are way bigger. Okay, so during a storm, our storm wave base may be right here. So every time there's a storm, my wave starts picking up more and more sediment as the bottom of my wave moves closer inland and runs into the bottom of the ocean. It starts carrying more and more sediment closer to land. So what happens is about every time one of those waves dies, it drops sediment here off the coast. And it just builds and 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 builds until you make a pile of sand or other sediment large enough to poke up above the sea level. Storm after storm after storm after storm. And this makes a barrier island. Behind the barrier island is a lagoon or a bay. On the other side of it, open ocean. Who can tell me where this is right here? Not Japan. Not the Caribbean. Not Asia.
Oh, it's near Australia.
Huh? You may. Huh?
It's near Australia.
It's not Australia.
I'll guess if you did.
Okay, your first guess will be after I tell you what continent it's on. You guys think that's true?
Yes.
It's on North America.
Oh.
Oh,
No, it's not. No, it's not.
it's in Mexico.
It's not the Gulf of Mexico. It's not Chile. That's in South America. Any guesses? Where do you think this is? It's not Australia. It's on North America. Huh? New York is closer, but no.
Oh, Maine.
Not Maine. Close. Yeah. Not Florida. Good guess. Any other guesses over here? Not Vermont.
Wait, it's Rhode Island.
It's not Rhode Island. Not New Hampshire. Man, we're just going through the whole list.
Delaware? Yo, I swear I said this.
You swear you said this?
I said Florida, bro.
Huh?
You're such a goon.
No. Are you just like searching along the coastline? No. Yeah. Yeah, sure. This is Massachusetts. This is the east side of Massachusetts. You didn't say that. Get out of town. All right. What are we looking at here? This is Gloucester Bay. How many of you guys like clam chowder? Any clam chowder lovers in here? I absolutely adore clam chowder. It's amazing. I love seafood. If you want the best seafood of your life, walk along this coastline here. There are dozens of little restaurants where they just make fresh chowder with whatever they caught that day. Oh, it's perfect. Okay. So I lived in Massachusetts for 2 years. Okay. So this is a glacial. The core of this is actually a glacial moraine that was deposited a few ice ages ago. Okay. But what's been thrown on top of it? Longshore current is going that way. Okay. So we have a buildup of these islands out here from storm activity. These islands are barrier islands. Okay. Barrier islands. Okay. Making protected coves behind them. On top of this core of glacial till that's been deposited as a glacial moraine, more sediment has been thrown on top, making a protected zone here. And then even after that, this sort of elf shoe shape. This is another, we call this a spit, but this is essentially a barrier island that got stacked up against this and has started curling over on itself because more and more sediment is constantly being thrown on top of it. It's made this perfect safe harbor. This is where many of the first colonization ships that came to the Americas in the 1600s landed. Okay? And by the way, some of the best fishing in the entire continent historically has been here. It's been overfished, obviously, over the hundreds of years. Still pretty good, though. But before, oh man, maritime industries thrived off the fishing from this bay. Okay, that's why it's so famous for its seafood. All right? Okay, so that's Massachusetts. This is how you get barrier islands. Anyone else, can you name any other barrier islands that might be more relevant to us? Bahamas have some, but I'm talking about closer to home. Huh? Galveston Beach. Yeah. How about the Gulf of Mexico? Padre Island. Padre Island is a barrier island. All of those long, thin islands that stretch between the coast of Texas and Mexico, along the edge of the Gulf of Mexico. I keep calling it the Gulf of Mexico. I'm just going to keep calling it the Gulf of Mexico, because who really cares, right? I'm not calling it the Gulf of America. I can't remember that. Okay? All along the Gulf of Mexico, all those little thin islands, those are barrier islands. And between them and Texas, lagoons. Everyone loves to go jet skiing. Everyone loves to go fishing. Everyone loves to go swimming in those lagoons, right? It's become a whole sport, sport and recreation-centered area over there. Okay, so we've established that there are powerful forces of weathering and erosion that change our shorelines. Do you imagine that that impacts us in any way? I mean, I've already shown you a few pictures of how it does, right? No one wants their house to be on stilts in the water. No one wants their roads to get washed away. It's pretty clear that we don't want these things to be happening. So what can we do to stop it? First of all, is there any stopping the ocean?
Move your house back.
Move your house back?
Don't like.
Very expensive, but possible.
Don't build your house off the shore.
Oh, how easy it is to say that now. How easy is it to say, don't build your house there, forehead? right? But it's not that easy after it's already built there. There are already tons of communities built up in places where shorelines are threatening them. So there have to be some ways that we can at least slow it down. Cannot stop the ocean. Unstoppable force. But we can slow down the effect. So let's talk about some ways that we do that. Jetties are walls that we build up perpendicular to the shoreline, usually around some waterway. Like in this case, a river that we really don't want to get blocked up with sediment. Look, how about this real life example? Look at all the boats that are docked on this side of the river. Maybe this is used for mercantile transport up into the continent. Who knows? But for whatever reason, it was worth protecting with jetties. What does a jetty do? Well, as longshore current is pushing sediment that way, it piles up against this jetty. Now, this only works for so long. What's going to happen eventually? It's going to go past it. It's going to build up so far it goes past the edge of the jetty, and that's exactly what's happened here. This jetty ends right here. The sand has completely overwhelmed it and is now, once again, closing off that waterway. What's the solution there?
Get some shovels and start digging.
Get some shovels and start digging? Sure, let's get all the Boy Scouts. Keep them busy. I was a Boy Scout. Huh? Yeah, I was a Boy Scout. I'm very familiar with the service projects that are fully just intended to keep young men busy. No. What was your suggestion? Build another jetty? You mean like extend this out more?
No, well, kind of, but like going that way.
Going this way?
Yeah.
But that kind of still closes that off.
No, like, you see, like it's going like diagonally.
Mm-hmm. Right, out that way.
Yeah.
But again, that doesn't really keep this open if we keep this out. If we...
The other side.
This side?
Parallel to it.
Going out that way. Well, our sand would keep building up out here and still threatening the entrance. At that point, just move. What I'm trying to get across to you is that, once again, we cannot stop the ocean. It only works for so long. Our solutions are either dredge that sand up and take it somewhere else, and therefore remove, kind of reset this whole situation, right? But again, it's going to keep building up later on. Or make your jetty longer. But why is that a bad solution? Why is that a less ideal solution, to make our jetties longer?
You're making like the water rise because you're putting more stuff in the water.
Not nearly enough. You're not putting nearly enough stuff in there to make the water rise.
Over time, it's still gonna catch up.
It's still going to catch up, true, but what's the other more obvious solution or reason?
Cost.
Yeah. The further out you go, the deeper it gets. The more expensive it is to make your jetty go that far out, right? Instead of building your jetty in 50 feet of water out here, you're building it in 100, and then 120, and then 200. Depending on how far out you want to go. Further out you put it, the longer it'll be before it gets overwhelmed, but it's still eventually going to happen, and is the cost worth it? Yeah, of course. All right? So, not a perfect solution, but there are no perfect solutions, only delay tactics. The next one is a groin, which is essentially the same concept as a jetty, except we don't really put it in front of waterways. We just kind of make pockets with it, okay? So you put little walls, usually of alternating lengths, out here along a coastline like this. Our longshore current is going this way, and so you're going to get a buildup of sediment inside of each one of these little groin pockets there. Okay? And it preserves this shoreline. Why are we interested in preserving this shoreline? Yeah, look, there's a community. You let that go for a few more years, and the shoreline is in backyards. Not a perfect solution, still just a delay tactic. Eventually, this buildup, it's going to build up, right? And these will get overwhelmed, and then we have a totally different problem, right? But it works. It works. Then there are breakwaters. A breakwater is more or less a wall that you build to absorb the energy from the waves before they ever even hit the shoreline. So this is a breakwater right here. Why is it there? Well, there's a boat anchorage right here. There's a whole dock. Waves are coming in this way, and where they would run into that dock and that boat anchorage, instead they're running into a breakwater. So if this is the surface of my ocean, a breakwater is basically a whole bunch of giant plastic buoys, like gigantic islands, like the size of this room. Okay, you make out of plastic, and then you anchor to the sea floor via chain. So when my wave runs into it, the top of the wave expends its energy on this buoy, and the bottom, without receiving more energy from the top, kind of dies out. And so on the other side of my breakwater, calm water. It's breaking the energy of the wave before it reaches the land. This isn't effective on a mass scale because it costs a lot to build and install these things. So you usually just use them for small circumstances, like protecting very specific areas instead of long stretches of coastline. Okay, but that is another method. But let's assume that we don't do anything to protect our coastline. Longshore current does its thing. It brings a lot of sediment, but it also can take a lot of sediment. When your beach or your shoreline has a lot of sediment removed from it, you only have one option: put more there, especially if your beach is a major part of your economy, like in Florida. These are pictures from a beach in Florida. What has happened? Yeah. Which one of these is the older picture? The one on the right. Why? Less buildings. Buildings aren't as tall, right? The one on the right is the older picture. I don't know which beach this is. But sand, gone. Carried away. What's your option? Where does Florida get most of its money? Tourism. People go to Florida for the beaches, right? They don't usually go for the alligators, right? They go for the beaches. You're not going to make a whole lot of money if your beach looks like this. So I have no choice but to bring more sand. And every now and then, they have to. They have to bring more sand to make it look like that. Okay? It's enormously expensive and takes a while. But then they've got 50, 60 more years of good tourism before they have to do it again, right? You can see they've actually built groins out here to try and slow it down. But it took people a while to figure that out. Yeah, of course. Hurricanes have a massive effect on shorelines. They are extremely powerful forces of wind, of rain, and storm surges. Okay? That wind can reach up to, where do I have it? 250 kilometers per hour. And I don't know what the strongest wind you guys have ever felt is, but that's enough to roll your car down the street. Like, not on the wheels. Roll your car down the street, depending on the size of your car. I'm talking about like a sedan, right? Very powerful, extremely destructive, gives a lot of energy to the water, and pulls a lot of sediment just by power of the wind itself. Okay? So that will change your shoreline based upon the power of your hurricane's wind. Then you've got the rain, up to 48 centimeters a day. That's a lot of rain, guys. 48 centimeters everywhere. I think the most rain we've ever gotten here has been a few inches. It's maybe 10 centimeters, if that. And then we had some terrible, terrible flooding. It's been a while since we've had that. But it's awful. The flooding that comes with a hurricane leads to a lot of runoff, and that runoff is going to carry a lot of sediment with it. Okay? Yeah?
Is that why Florida, like, the beaches go faster?
No. The beaches go, like, loose sediment. The sediment moves away fast in Florida because of longshore current. Hurricanes don't even have to do anything. But when hurricanes come in, they do have a big effect on that. Okay? But the storm surge, do you guys know what a storm surge is? What is it?
Where all the water starts rising.
Why does the water rise?
Sea level.
Sea level. Sea level's not rising.
That's really like the hurricane, like, it makes the water go up.
The hurricane makes the water go up. You are correct, but I'm wondering if you know why. Yeah. Yeah. Any ideas? Okay. Inside of a hurricane is an extremely low pressure zone. So if this is the surface of my ocean and my hurricane is hanging out right here in the atmosphere, then below that hurricane, or inside of that hurricane, is an extremely low pressure zone, meaning that the water inside of that boundary is going to bubble up a little bit because it's not under the same amount of pressure as the rest of the ocean around it. The air pressure is less. It's going to bubble up a little more. Yeah, that's inside the hurricane.
No, like the center of the hurricane.
Oh, and the eye? Yeah, much closer to the eye. It's not exclusively within the eye, but it is included within the eye, okay? A simple way to explain this is if you have a glass of some beverage with a straw and you start sucking on the straw and then put your finger over it, you have reduced the pressure inside of the straw and my liquid is inside of the straw above the level of the water inside my cup, right? That's essentially what's happening here. Straw, low pressure zone, bubble of liquid inside of straw. Now, depending on how severe my hurricane is, and therefore how low the pressure is, that'll determine on how high my storm surge can get. They can get pretty high. I think I have, yeah, between 1 and 6 meters. Guys, 6 meters is 20 feet. That's a really high storm surge. What happens when that storm surge hits land? Yeah, how high up does it go? 20 feet inland. Not 20 feet up the shore. It goes all the way up to 20 feet above sea level. Which, when you're in a city called New Orleans, which is typically between 7 and 10 feet below sea level, how bad is that? Pretty bad, which is why they have really, really bad flooding every time there's a major hurricane that goes through Louisiana, right? Okay. It happens. Hurricanes have dropped fish hundreds of miles inland.
So they can drop alligators from out the sky?
Alligators, as far as I'm aware, have never gotten sucked up into a hurricane, but fish have from the ocean.
I like the fire tornadoes and all that.
Yeah, we're not going to discuss the merits of things like fire tornadoes or Sharknado or anything like that. Okay? That's its own completely different brand of fiction, which is fun to watch, but absolutely preposterous. You know? Real fun to watch, though. All right. I lived in Louisiana for a couple years while I was getting my master's degree at the University of Louisiana. Oh, look, I'm actually wearing my Raging Cajun shirt today. That's a coincidence. I almost wore my beige pants, by the way. I was walking out the door, and then I realized I look like Jake from State Farm. So I went back and changed my pants. Yeah, I should get a State Farm name tag, right? Okay, so, Aaliyah's not even here, and we're talking about what she was mentioning earlier. How tectonics can affect the shorelines, okay? So we have two different things, emergent and submergent coastlines, okay? So an emergent coastline is one where tectonically the land is rising out of the ocean. And then in a submergent, it's where tectonically it's getting lower into the ocean. Under what circumstances would I have an emergent coastline? One word is coming out of the ocean. Was that an idea? Do you have any ideas? Well, even so, do you have any ideas? I want to hear from you. Huh, what?
When the water level goes down,
And we're not talking about a change in water level. We're talking about a change in the land. Yes, this is a tectonic subject, but what's happening?
Tectonic plates
Huh?
hitting each other?
Yeah. Good. You both said it at the same time. So, convergence, tectonic plates hitting each other. And this is causing one or both plates to rise up higher, right? Out of the ocean in this case. This happens a lot along, say, California, where the Pacific plate is subducting under North American plate. It causes a little bit of uplift in the North American plate on top of it. Some parts of California are actually gaining several inches of land every year as a result of this submergence. Well, hopefully no one's living close enough to the ocean to notice a few more inches every year in their backyard. Right? But it adds up over, 1,000 years or 10,000 years, right? 10,000 inches is a lot more noticeable than one. Geologically speaking, 10,000 inches or 10,000 years isn't even the blink of an eye. Not even a second. 1,000,000 years is a blink of an eye as far as geology is concerned, right? Okay, what about a submergent coastline? One where land is sinking into the ocean.
Tectonic plates go apart from each other.
Good thought, but no.
The one where they like,
Huh?
Hispanic ones.
Transform? No, but good thought. It's a different process.
So an ocean moves inland.
Again, we're not talking about sea level change.
What was the question?
A submergent coastline is one where land is going deeper relative to sea level.
Is it because it's they're like hitting each other, but one of them's like going down under it?
So submergent, again, good thought, but no. What's happening as I pile more and more sediment on top of sediment, on top of sediment, on top of sediment, on top of
Roll
sediment?
down the side.
Yeah, they start compressing down. The weight on top causes compression down below, and so we start to see a decrease in the elevation. As you are squeezing water and air out of all the sediment down below, it starts to compress. Sea level can move further inland. This happens along what we call passive margins, okay? The east coast of North America is a good example of this. Who can tell me where this is?
That's in Delaware.
Oh, good. Yes, excellent. It is in Delaware and Maryland, right? And Virginia. And there's New Jersey. Jersey, right? Senor Jersey. Okay. I apologize to anyone from New Jersey for mocking your accent. It's just so easy. Okay, so I actually used to live right in here. I don't remember exactly where in there. But there's a town there that I used to live in for a couple of years as a kid. Absolutely loved it. Havre de Grace, Maryland. Super cute, super quiet, super historical. They had Renaissance fairs and pirate reenactments, and it was a blast. Highly recommend a visit if you ever go to Maryland, okay? This is Chesapeake Bay. What does it look like? Does it remind you of anything in its shape and its structure?
Like roots.
Roots? Okay, so it has that dendritic structure we talked about before. Neurons, leaves, all of these things that share that same sort of branching dendritic structure. Fascinating. I told you that shows up a lot in nature. It really does. There's a whole lot of implications for that, but we won't go into that in this class. But what else does this look like to you? Please, don't kill my students. I understand the impulse, though.
The rivers connect to the ocean.
A what?
The rivers connect to the ocean.
It looks like a river.
River bend.
Yeah, it looks like a river. That's because it is. Or it was. This was a river system that went all the way to the ocean. It's now a saltwater bay. Why?
Connects to
What must have happened to this part of our continent? It's a submergent zone. It is sinking slowly into the ocean. And therefore, my river got flooded by the ocean and is now Chesapeake Bay. Now, this river still flows into it. This river still flows into it. This river still flows into it. But this area has sunk so far down that the ocean infiltrated, invaded this river system all the way up here. That's what Chesapeake Bay is, because it is submergent. Yeah.
You see like the two endpoints, like the top of where Delaware is at? Is it possible to like connect Delaware?
Here and here?
Yeah. It's like possible will they connect?
Oh yeah, they absolutely will. At some point in the future, this is going to be overwhelmed as well, and then this will be an island.
So it's like float off.
So Delaware would be an island?
Or like
I mean,
float away?
Kinda, I guess. Yeah, Delaware could be an island. It's kind of treated like an island already. It's only connected to Maryland here. Like, I don't even know why is that there? Like, come on. Do you know how silly some of our state boundaries are? They're pretty silly. I don't have time to explain to you some of those examples.
Delaware or Maryland?
Yeah,
So Maryland is over there.
and this is Virginia. Yeah.
You think people would complain if they like changed them?
Oh, it's not going to change. There would have to be some pretty crazy national upheaval to change state boundaries. The last time that I can think of that states argued over their boundaries in any meaningful way was shortly after, let's see, I want to say it was maybe, I don't remember the year. I want to say it was a decade or two after the Civil War. Ohio and Michigan went to war with each other over a strip of land connected to one of the Great Lakes. They both wanted this strip of land because it was prime fishing real estate. They both wanted that in their economies, and they both laid claim to it, and it got so bad that they actually mobilized their own militias, and they were shooting at each other, Ohio and Michigan. The federal government had to step in and say, hey, knock it off. This part goes to you, this part goes to you. And that's why Ohio and Michigan actually still kind of despise each other. If you've ever watched an Ohio-Michigan football game, they get bad, guys. And it's all coming from that war a couple hundred years ago.
So for some fish, they still hate each other.
I mean, yeah. Yeah, like it's gotten so bad that when the Ohio team, Ohio State, goes to play at Michigan University of Michigan, they have to have security as they walk them into the stadium because there are mobs of people trying to tackle them and take them down and stuff before the game. And vice versa, when Michigan goes to Ohio, the same thing happens. Yeah, it's rough, it's bad. Okay, so now let's talk about sea level change. How can I tell simply by looking at layers of rock whether sea level has risen or fallen? It shows me. Good. How? Does it whisper in my ear in a soft, sweet voice? I mean, sometimes I hear that when I talk to a rock, but not in this case. How can I tell by looking at layers of rock whether my sea level has risen or fallen? I'm not asking you to interpret it. I'm asking you to tell me how I might be able to tell, huh? Yes, whether the water level has changed or fallen. I'm looking at layers of rock that represent what the environment was like 100 million years ago. My environment now is nothing like that. How can I tell what the water level was like 100 million years ago simply by looking at a layer of rock? Give you a hint. These are things that you learned about, in particular, as you were identifying rocks for lab.
Oh, the way it goes, like,
The way it goes.
never mind.
That's okay. There are no silly answers here. You have an idea, Emily? You're talking about the structures. Structures can be great indicators, but also, for the most part, they tend to be more specific. Like the ripples, like what you're talking about, that'll tell me maybe like what the wave activity was like, but not necessarily water depth. Possible, but not the more broad answer I'm looking for. Fantastic thought. Think a little more basic than that. Instead of the structures in the rock, the components which make the type of rock itself, right? It's the type of rock itself that will tell me. Shale, for example, very fine particles, microscopic. High energy water, low energy water. Remember? Low energy water. Why? Because if it was high energy water, those fine particles would never have fallen to the ground. They would never have gone to the ocean bottom. They would never have gotten incorporated in rock. Okay? Only in an environment where the energy is so low will those small particles fall to the bottom. They'll filter down to the bottom of the ocean and get turned into shale. If I'm looking at shale, I'm probably looking at deep ocean. Limestone. Shallow ocean. Why? Because it's made out of calcite. Probably from shells. Or if it's not made from shells, guess what? We learned that micrite limestone will form in warm, shallow seas. If I'm looking at limestone, I'm probably looking at shallower, probably warmer water. Sandstone. Near shore environment. How do I know that? Yes, it's made out of sand. And where do we find sand? Near continents, because that's the source of the quartz. Are you following the logic here? So I can look at the sequences of these rocks in a layer of, or in a whole bunch of layers of rock, and I can say this was deep water, this was shallow water, this was near shore, and I can see how that changed over time. Sandstone, limestone, shale, limestone, sandstone, shale, limestone. I can interpret the rise and fall of sea level, generally speaking, by simply looking at the sequence of these rock types as they are next to each other. We call that sequence stratigraphy, okay? When sea level rises, we call that transgression. When sea level falls, we call that regression. So right here, I have a transgressive sequence. Let's say that this represents 100 years ago. What do we have here? Shale. Or actually, right here, because this is they're showing us a more they're showing us a shallower water environment with a lagoon, but it doesn't explain it very well. But right here, their deep water sediment is limestone, and their shallower water is shale, and that's only because in a lagoon that would be the case. Okay, this is sand. Okay, then we've got our deep water sediment on top of our shallow water sediment, on top of our near shore sediment, okay, the sandstone, okay, right there. If I were to drill right here after 100 years, I would see deep on top of shallow on top of near shore. Deep, shallow, near shore. Law of superposition. Whatever's on top is younger. Whatever's on top is youngest, right? So if the deeper sediment is on top, that means what? The older sediment is younger, is deeper, sure, but well, how can I interpret that? If I'm seeing the deepest sediment is on top and the shallower sediment is on the bottom and therefore older, what's happened? Sea levels rose. We had a transgression. What about the opposite? Yeah. If I am seeing deeper sediments on bottom and shallower sediments on top, the most recent thing that's happened is the deposition of those shallower sediments, and therefore a regression happened. What if I see them in sequence? What if I drill right here? So I'm seeing sandstone, shale, limestone, limestone, shale, sandstone. Transgression followed by a regression, one after the other. Oh, my friends, this opens a whole new world of interpretation. Sequence stratigraphy is really cool. We use it in so many different aspects of geology to interpret our Earth's past. This is how we can do things like give approximations for sea level hundreds of millions of years ago. Any questions about that? Any questions about shorelines at all? Let's talk about tides for a moment. We already talked a little bit about that. Tides in general are caused by what?
The moon and the sun.
Primarily the moon, but like we talked about earlier, if you remove the moon from the equation, there would still be tides just from the sun. The word tide itself doesn't actually have anything to do with the ocean. Tides exist outside of the ocean. Tides exist in your head. Tides exist in space. Tidal forces are tied to gravity. we just generally refer to the tides in the ocean because that's the most obvious manifestation of that to us. But there are tidal forces in space. And, I mean, the moon has a very slight tidal force on your head. Bless you. They've actually measured this. It's nowhere near, it's almost not too small to calculate. But when the moon is directly over your head, our heads, ever so slightly, change their shape and are pulled ever so slightly towards the moon. Just think about how much water is in our heads. Okay? Ever so slightly. And I'm talking about like 0.000001 of a centimeter. Okay? Barely even measurable to an accurate extent. Okay? But still does it. That's a tidal force. So, what I'm talking about when I say tides as it relates to the ocean, whenever the moon is on one side of our planet, the water on that side of our planet is pulled towards the moon. You get a bulge of water towards the moon. Right there. That's the surface. This is obviously exaggerated. But wherever the moon is, you have high tide. Because the water is being pulled towards it, so there's a bulge on that side of the planet. Now there is also a bulge on the opposite side of the planet. Why? Because the water is getting pulled towards the moon, but the water on the other side of the planet is not. The water along the sides gets pulled that way, or is left over here. So high tide, high tide. And on the not the opposite, but on the sides of the planet at 90 degrees to it, where the water is getting pulled away from towards the side of the planet with the moon, you have low tide. And because the moon is circling our planet at a consistent measurable pace, we can know exactly when high tide and low tide will be every day. Because we know where the moon is at all times. It's mathematically guaranteed. Okay? A tidal flat is what we call it when all the water gets pulled out from a lagoon because of tidal forces, leaving usually just kind of a flat, muddy expanse for 6 or 7 hours at a time. Okay? Then the water comes back, covers it with water again, brings even more mud and sediment there. Okay? That's a tidal flat. Cool? Are you still doing on this 6-7 thing? I love these things that come and go within a few months. Give it 6 months. I don't even remember what that is. Okay. Let's talk about the ocean bottom to wrap up our conversation here. Okay? The earliest effort to study the bottom of the ocean was conducted in 1872. This mission started in 1872. It was the HMS Challenger. Okay? You guys know what HMS means?
What's the first word?
Her.
Her?
Her.
Her monthly salary.
Her monthly salary Challenger. No.
Her mothership.
Oh, you're so close. Her Majesty's ship. Yes, or His Majesty's ship, depending on who's in office. This was a British ship, a British mission on the HMS Challenger. Her or His Majesty's ship, right now it's His Majesty's ship because they have a king. But at this point in time, they had a queen. So Her Majesty's ship, the Challenger, went and did this mission where their job was to explore how deep the bottom of the ocean was. Prior to this mission, everyone just kind of took it for granted that it was probably a couple hundred feet deep, just deep enough you couldn't really see it. Who can dive that deep, right? There's some Polynesian, There's some Polynesian cultures where people actually can dive 60, 70 feet deep, just hold their breath and dive that deep. But nobody can free dive as deep as the deepest parts of the ocean that they thought. So they thought it was a couple hundred feet.
I thought you meant like scuba tank.
No. They didn't have scuba. Yeah. No. So this was the first effort to actually figure it out. How did they measure the bottom of the ocean? Well, they took a really long rope with them. They tied a heavy metal weight on one end and then put a knot every 6 feet on the rope. Then they would drop the rope over the side and count how many knots went into the water until it stopped, until that weight hit the bottom. You multiply the number of knots by 6, that tells you how many feet down it is. Clever, right? Pretty basic, but clever. Yeah, that worked until I ran out of rope because the ocean was a heck of a lot deeper than I thought it was. As soon as they realized that we're talking about thousands of feet, not just hundreds, they had to go back to port and get more rope. And that's when they realized how truly incredibly deep certain parts of the ocean were. There were parts that they could not carry enough rope to measure. Mind-blowing stuff in the late 1800s. Okay? For some... Oh yeah. Oh yeah.
How many feet is a mile?
How many feet are in a mile, my friends? 5,280 feet in a mile. 5,280 feet in a mile. What you were probably thinking about is 1,000 meters in a kilometer. Yeah, which is more scientifically, thinking more scientifically, so I appreciate that. Okay, that's imperial system. Okay, for some reason, I don't know why we still use the imperial system, but we do. We're one of the only countries that does. Okay, so now we don't do that. Okay, now we use something called bathymetry, which is the study of the ocean floor. Okay, but we use something called sonar. Have you ever heard of sonar? Have you ever watched one of those old war movies and they're in the submarine and they send out a ping? Bing!
Doesn't it like reflect off of objects?
Bingo, right there. Sound, navigation, and ranging. Sonar. Okay? What you do is you blast out a sound wave. Right now, I am emanating sound waves with my voice. And you're spilling glass. That made a noise. That noise traveled through the room just like my voice does right now. You all are picking up the sound of my voice in your ears. Your ears are intercepting those sound waves, transferring them into a signal that your brain can comprehend and making sense out of it. But at a more basic level, my sound waves are going throughout this entire room, bouncing off of objects and returning back to me. If none of you were in here and I was talking to myself, I would speak. My voice waves would bounce off of objects in this room, come back to my ears, and be intercepted.
Wouldn't it be louder?
So is that like echo?
That's what an echo is. When you're in a very large space and your voice waves are bouncing off of things and returning to you, that's why you hear this kind of double thing. It's bouncing off of multiple surfaces, some further away, some closer. So if I'm going, hello, 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 right? That echo, you're hearing the return of your voice to you across a longer distance from a different object further away. You all are actually hearing my voice right now. Some of you are hearing it, technically speaking, sooner than the rest of you. If I stand over here, I say, hey, buddy, how's it going? You heard that 0.000 seconds, 0.0001 seconds before Jackson heard it, simply because he's further away. He's traveling at the speed of sound. Speed of sound is still super fast, but you're still hearing it before he does, right? Not to be exclusive, but you know what I'm talking about, right? Okay, so this is how sonar works. You send out a sound wave. That wave reflects off of an object. You have a receiver, like our ears, that picks it up. Depending on what it bounced off of and how far away that object is, you will get different wavelengths back. So we send out sound waves under the water. They return to us, and we can draw an image of what the bottom of the ocean looks like based on how quickly those waves returned to us. That's how we use sonar. Now here's the cool thing. This doesn't only work for surfaces. We have figured out how to use this underground. Yeah. This is called seismic interpretation. You use seismic, or you use sound waves to make a seismic profile to figure out what my different layers of rock are underground. Because it turns out that these waves also will return at different frequencies and wavelengths depending upon the type of material they bounce off of. So if I make a loud noise, like an explosion underwater, those waves will travel through the rock, and then I have receivers in the rock I can analyze the frequencies and wavelengths that come back, and I can see what the different layers of my rock underground are. Maybe it's limestone, sandstone, shale, limestone, sandstone, shale, 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 limestone, sandstone, whatever. Each one of those materials is going to return a different signal back to me. And through lab testing to figure out what each one of those materials is going to return to me, I can then draw a pretty accurate underground image of what I'm looking at. This image is interpretation of this seismic profile, which looks like a lot of white noise to you, but if you look at it for a minute, you can start to see the patterns, right? You can see this low right here, and you can see this high right there. And with enough study and practice and experimentation in a lab, you can draw something like this as an interpretation by looking at that. Okay? We use this in the oil industry all the time. All right, let's talk about the ocean floor and its different areas. Okay, so you divide the ocean floor into three basic areas. Continental margins, which are the areas obviously close to continents. Deep ocean basins, which are these big, wide, flat, open areas in the middle of our oceans. And then you've got your mid-ocean ridges, where you have divergent plate boundaries and new plate material is being made as it pushes further and further apart. So you've got your continental margins. You have passive margins, what I talked about earlier with your submergent coastlines. Okay, those are passive margins. There's nothing tectonically happening there except the subsidence of your continent as more and more sediment is piled on top of it. Okay. Then you have your active margins. Those are going to be the places where you have actual tectonic activity. Submergent or collision, right? Interactions. That is an active margin. There's something tectonically happening there. Okay? So here on our passive margins, clearly you can see that there really isn't anything tectonically interesting going on, just a buildup of sediment. We have the different areas. We've got our slope, our shelf, which is basically just flooded continental crust. Whenever the sea level is lower, this is actually just straight up continent. During the last ice age, Florida was twice the size it is now. Okay? And it's getting smaller as sea level continues to rise. Florida is going to be practically non-existent eventually. Okay? But it was way bigger than it is now because a lot of it is flooded at the moment. Okay? Then you've got your continental slope, which is this area here, which is mostly continental sediment that's getting pulled out to sea by this activity, by the wave activity, by gravity as it's going downhill further out into the ocean. Okay? And then you have your continental rise, which is this more general slope here, mostly ocean sediments on its way as the slope is, as the rise is kind of increasing its angle up towards the slope there. Then you've got your deep ocean basins. In an active margin, you'll typically have some subducting plate, which is going to create volcanism on the coastline of the overriding plate, like we've talked about. But you're going to end up with an accretionary wedge right there, which is basically all the stuff on top of this subducting ocean plate that's getting scraped up on the side of your overriding plate. Where your ocean plate is subducting, and between that and your accretionary wedge is often this super deep zone that we call a trench. The deepest parts of the ocean are in these trenches. The deepest trench, I think I actually have the statistic on here. The Mariana Trench, yeah. Yeah, right here. The deepest trench is Mariana Trench, 36,000 feet. Did you say 14 feet?
No, you said 14,000.
14,000? More than twice that.
How long does it take to travel a mile?
How long does it take to travel a mile? I don't know. How lazy are you?
No, like on the vehicle.
I don't know. How fast are you going?
Regular speed.
Regular speed?
Regular speed?
Like 60.
If you're going 60 miles an hour and you're asking me how long it takes to go 1 mile, divide 60 miles an hour by 60 or by 1 mile.
1 mile.
Yeah,
Do the math.
You said 1 mile is 5,000 feet.
5,280 feet.
So we can drive down the bottom of the ocean like
Yeah, bull crap.
At 60 miles an hour?
Yeah.
Who has a calculator? Let's help him out.
No, as soon as you go start moving, you're gonna pull a
Seriously, who has a calculator?
Titanic.
Let's make you do the math. 36,163 divided by 5,280.
That's so wild.
5,000.
5,280, the number of feet in a mile.
Yeah, 6.8.
6.8 miles. Okay, so going at 60 miles an hour to go 6.8 miles.
6 minutes.
6 minutes?
This guy.
How would we figure that out?
Divide it.
Yeah.
By what? Oh, by 60.
Your speed by the distance.
0.114.
0.114. So it would take you 0.114 minutes, or hours, I should say, to go 6.8 miles at 60 miles an hour. So now multiply that number by 60, and that tells you how many minutes.
6.8.
6. Okay.
I have 6.8. I multiplied it again.
Okay. I'm not sure what the point of that exercise was.
That means like we travel down the very bottom like 6 minutes.
If there was a
If you're going at that speed, sure, yeah.
Like just vertically straight down 6 minutes.
Yeah, so you chose a unit of an hour, which includes 60 minutes in it, to go at 60 miles an hour, to go 6.8 miles. If you were driving in your car, yeah, that's how long it would take you.
What was the
My
submarine
house is
that like
farther from that.
The submarine that got squished, are you talking about the one that went to the Titanic?
yeah.
Wasn't nearly this deep. Yeah, those people got squished like pancakes. And I don't mean to be insensitive, but
Like if the
that submarine got squished. And it wasn't nearly as deep as this.
like if it was just a vertical road down.
If it was just a vertical road down, yeah. But except your car would be the size of a ramen noodles cup by the time you got there.
My house is further than 6.8 meters.
Like if you were flying, it'd be. But it's like you have to go differently.
So, let's continue our conversation. Okay, so deep ocean basins cover about 30% of the Earth's surface. There isn't a whole lot interesting in them, except for things like trenches, seamounts, shipwrecks, stuff like that, okay? The deepest trenches are out here. Here's the Mariana Trench right here. Here's the Japanese Trench. The Tonga Trench is also pretty deep. The Philippine Trench is very deep, right there. There is a trench over here along South America. Not quite as deep, but still pretty decent, okay? But these are the deepest places in the ocean, with the Mariana Trench obviously being the deepest. Okay, a seamount is a volcano out in the middle of the ocean. Now, there's somewhere between 1 and 2 million of these things, but we can't really get an accurate count of them. And it's extremely hard to try and monitor all of them, so we really don't. Then you've got your flood basalts, which are these big, shallow water areas, usually next to volcanic islands, where volcanic basalt has spilled out into the ocean and has kind of built its way out into the ocean, but has not gotten high enough to come above the ocean surface. We call those flood basalts. They make basalt plateaus out in the ocean. Okay? So our mid-ocean ridges are where plates are splitting apart from each other. And each one of these lines here represents one of those mid-ocean ridges. See, here is the mid-Atlantic ridge. The one that I showed you goes through Iceland. It slices Iceland in half. I showed you those pictures of me hanging out inside of the mid-Atlantic ridge right at the beginning of the class. This East Pacific ridge is an extremely aggressive ridge system. That's why it's colored so red. It's moving extremely quickly, making a lot of material. But yeah, everywhere you see one of these ridges, things are splitting apart, which is why you can see this mid-Indian ridge splitting Saudi Arabia from Africa right there. That's why we've got the Gulf of Oman and the Red Sea right there. Okay. Okay, so this is showing you a cross-section of mid-ocean ridges and how they start. So our oceanic crust it's a thick layer of basalt and gabbro, more or less. And then you start getting the convection cells underneath of it going in opposite directions. you start getting faulting and fractures here along the top as the pressure to spread them apart increases, and eventually that fracturing, ridging, faulting system causes a separation between the two plates, and you get new material that comes up between the two, and it adds to both sides, pushing them further and further apart, adding new igneous mafic material to both sides of these plates. This is what a cross-section of the ocean crust looks like. So here at the top, we've got our water, obviously. Underneath of that is whatever sediment has been deposited on top. Bless you. Underneath of that is the basalt that's been deposited through volcanic activity at the ridges. Then underneath of that is a dike complex. Someone remind me what a dike is.
Like a ridge.
It's not a ridge. Remy, do you remember? No?
Oh, it's like the little mountain ranges that come off volcanoes or something?
It's like the,
It has to do with volcanoes.
Is it where it branches out?
Yeah, it's one of the ways that magma will remove itself from a magma system, from a magma chamber. But in what way? Not vertical.
Diagonal.
This is, a different word.
Horizontal.
oh, zigzag.
No. Perpendicular to the original layers of rock. Yes. Yeah. You went diagonal. I could tell where you were wanting to go with that. It was just a matter of the right word. Okay? So, a dike is when magma separates itself from a larger body of magma, and then splits away from it and cuts perpendicular to whatever layers of rock were there before. These are the dikes, the conduits for magma from magma chambers beneath the mid-ocean ridge system that deposited the basalt on top. So why are they out here? They're getting shoved to the side the same way that the basalt on top is by newer dikes forming at the active margin, at that divergent plate boundary. The old ones are getting shoved to the side just like everything else. So we have sediments, basalts, dike basalts, underneath of that, gabbro, which is, remember, the intrusive variety of basalt. Same composition for the most part, just intrusive, formed underground instead of at the surface. Underneath of that is some layered gabbro because it's under quite a bit of pressure, and then mantle underneath of that. I already talked about this when we discussed metamorphism, but a quick recap. This is a black smoker. This is what happens when water makes its way down into these divergent plate boundaries, dissolves metals from these newly forming mafic minerals, so it's pulling the irons, the magnesiums, and all this other stuff out of it. It leaves behind hydrometamorphosed metamorphic rocks, things like talc schists, serpentinites, things like that, okay? And all of these dissolved metals in this boiling hot water get pushed back up to the surface by the pressure from deep underground. When that boiling hot water gets pushed out into the freezing cold water at the bottom of the ocean, what's going to happen to all the dissolved stuff? It precipitates. This isn't smoke, that's all metal, okay? And it gets deposited there at the bottom of the ocean. Okay, so how does an ocean basin actually develop? These oceans that we have today have not always been there. Continents form, they break apart, they split apart. Continents reform, they split apart. Where the Atlantic Ocean is right now, there used to be a massive continent called Pangaea, right? But now we have the Atlantic Ocean. What happened? How do continents split apart? How do they come back together? Tectonics. Well, what's the tectonic component for the splitting apart process? So we have some convection cells that start going in opposite directions underneath a continent. This is going to stretch and thin the continent above that interaction zone. As our continent gets stretched thinner, it starts to crack, it starts to break, it starts to make faults. What comes up through those cracks and breaks? Magma. Initially, felsic and intermediate. But as my continent gets stretched thinner and thinner and thinner, Bowen's reaction series doesn't have as much time to work. And so we start getting slowly more and more mafic magma making its way to the surface. Mafic magma on the surface is going to cool and make mafic rock. Mafic rock is denser and thinner as a crust. And therefore, as more of it gets spilt out onto the surface of this continent, our continent, rock in that area, is going to get denser and thinner, which means it's going to be a lower lying area, which means that water is going to start collecting in it, and eventually the ocean is going to start spilling into it. So our continent gets stretched thinner and thinner and thinner until mafic rock, this black rock in this picture, starts getting deposited. Water starts building up inside of this lower area, this big thick valley that we've got now. And then that valley eventually widens out and becomes an ocean. We can see that happening right now in Africa. The Red Sea is a perfect example of this happening. Right now, it's at this phase, this linear sea phase. That's what the Red Sea is. It is still splitting apart. There is going to be a much larger sea there eventually. Yeah.
Is that like how Africa, like, decided is breaking off?
Yeah, so the Arabian Peninsula used to be connected here. It has already split apart. It's only connected by the Gulf of Sinai, or the Sinai Peninsula right there, right now. Okay? There is also a split happening right here that's going to pull East Africa away from West Africa eventually. Okay? It's happening right here and here and here. That's why there's all these lakes and valleys in this area, because it is actively splitting apart. Any questions about that? Any questions about anything today? All right, well, that's it for lecture. That's it for lecture 11. That wraps up module 2. Remember, starting now, your lab exam opens. Starting on Tuesday, your exam 2 opens. We will have an exam review on Tuesday. Online students, hopefully you're watching this before Tuesday. If you have any questions about module 2, please send them to me in an email, and I will address them during our exam review on Tuesday. Great. Any other questions before I end this recording? All right.